Okay, so last time in the previous video, we verified that things were exact. We reviewed partial derivatives. So what I want to do now is actually solve that differential equation. So on that second page of your handout, number 1 and 2 on that page are exactly the 1 and 2 that we showed were exact equations. Okay, so here's going to be our plan of attack. We're going to work with the m portion, the left-hand piece, and I'm going to integrate. And I'm going to integrate with respect to that variable. And I'm going to get a potential or a part of a big function f that I'm then going to differentiate and with respect to the other variable and make it look like this and kind of see anything that's missing that I need to look at. All right. So I'm ultimately looking for a function of both x and y. And to start with, I'm going to integrate this m portion, and I'm going to integrate it with respect to x. All right, so in the previous problem, to check that it was exact, we were differentiating with the other variable than the dx. Now I'm integrating with respect to x, which means I'm integrating 2x plus y with respect to x. All right, so normally when we do integration, we always at the end, your teacher stressed to you to include that constant of integration, and that's still the case. That constant is going to take a little bit different form now, so just hang on to that idea. All right, if I'm integrating with respect to x, so if I integrate 2x, that integrates into x squared. Y, remember, I'm pretending that it's a constant, so a constant integrated with respect to x is just x times that constant. And then normally right here I have a plus c, except in this function, what I'm going to do is to have some function only of y. All right, remember what I'm doing. I'm looking for some big f function whose derivative with respect to x is this piece, whose derivative with respect to y is this piece. Okay, so I've got to allow for this function that is only a function of y. All right, so now what I want to do is to take the partial of f with respect to y. I just integrated with respect to x. Now I'm differentiating with respect to y. So the derivative of x squared, again, x is a constant. The derivative of x squared is 0. The derivative of xy with respect to y is just an x. And the derivative of g of y is just g prime. So now what I want to do is I want to say, okay, I need that function to look like this function. So I need that derivative with respect to y to look like what I started with up here. And most of the time the stuff will be there. If it's not, that's where we'll find this g of y term. So x squares, they're both there. I can get rid of them. So really all I've got left is a g prime at y is equal to negative 2y. So let me integrate g prime with respect to y, and then I'll essentially be done. So the derivative of negative 2y is a negative y squared, now finally plus some constant. So together this piece and this piece make up my function that I want. So my answer actually looks like everything in the f function, x squared plus xy plus the g of y, which is down here, which looks like minus y squared plus c. All right, think about what your check would be for this, and that's my answer. My check would be if I differentiate that with respect to x, do I get this? And if I differentiate all of this with respect to y, do I get this? And you will. That's our procedure each time. We're going to integrate with respect to one variable. We're going to differentiate with respect to the other variable and create that function. Look at number 2. So again, to start with, to find that f function, I'm going to integrate the m portion with respect to x. So again, anything with a y that's a constant, we're integrating x's. So the integral of the cosine of x is actually the sine of x. Cosine y is a constant. And the integral of 2x is x squared. Plus some g of y function that I'm going to create. Now, if I differentiate f with respect to y, I'm now kind of building on this other side. If I differentiate this function with respect to y, the only thing I need to differentiate here is the cosine of y. Derivative of cosine is a negative sine y, so a negative sine x sine y. The derivative of x squared, that's gone. And then g of y's derivative is g prime. So once again, I want to use this piece, and let's don't lose that negative sign. Running out of room there, maybe you can see. So I've got a negative sine x sine y. So that's gone in a sense. So what I'm left with is that g prime at y is equal to 2y. Kind of like the previous problem. I just picked a problem. I didn't know how they were going to work out. So g at y is y squared plus the constant. So again, the f function that I'm interested in is all of this plus the g function, which is down here, plus a y squared plus a constant. All right, that's going to be our procedure every single time. You know what's going to happen, though. I don't have to have, this doesn't have to be a dx in the first one and a dy in the second one. Anything can happen. We just use those variables to build and to follow the same procedure. So let's look at number 3. Number 3, I've got dt's and dy's. Okay. So the first thing I'm going to do is to show that this is an exact equation. So this is what I've called the m portion, and it's a function of t and y. And this is what I'm calling the n portion. So the first thing is let me differentiate m. Over here I was doing a dt. Over here I was doing a dt, so let me differentiate now with respect to y. So that means the only piece that I've got to differentiate is that little piece right there. The derivative of that is 1 et, and t e to the t, that goes to 0. And if I differentiate n with respect to t now, I start to write x, but with respect to t, the derivative of 1 is 0. The derivative of e to the t is e to the t. Therefore, indeed, this is an exact equation and I can pursue it. So let's do that. So I start by looking for some function of both x and y. I'm sorry, not x, I gotta have it. T and y. And I'm going to integrate, first of all, with respect to t. So I'm integrating e to the ty minus t e to the t. This integration is really nice. This one, not so much. So we'll need to review an idea from Cal 2 to do that. But this is essentially kind of expanded out, if you don't mind. This is a constant times that piece, right? That's e to the t dt, and I can integrate that. That's an easy formula to integrate. Minus the integral of t e to the t dt. All right, so this integration is just a y e to the t plus a constant. I'll just hang on to that constant. In the second piece, y'all, that's your typical integration by parts problem. So let me just kind of review integration by parts. Integration by parts is based on the product rule in calculus. So integration by parts, you might want to look that up. Integration by parts says if I want to integrate u and a dv term, that's equal to u times v minus the integral of v du. All right, so to make that happen, I need to identify something as a u and something as a dv, and then I'm going to integrate or differentiate accordingly to find all these other portions. So we're working with this piece. Let me just go here and think about that. All right, so I'm going to choose for my u, I'm going to choose my u to be just the t. Let me tell you why I chose that. And experience is a great teacher here, but I know I'm going to need a du. So typically, I want to choose something here that gets simpler. The derivative of t is just 1 dt. So that certainly got simpler. And then if I choose e to the t dt for my dv, and I integrate to find v, well, that's an easy integral. All right, so this problem is exactly the same problem then, using this formula. It's equal to uv minus the integral of v du. Again, this has already been integrated. I can integrate this. That's an easy formula. The integral of e to the t is an e to the t plus the constant. So back over in our problem, all of this then gets put in over here for this term. So minus t e to the t minus e to the t plus the constant. So this actually looks like y e to the t minus t e to the t plus e to the t. And in this next piece, it's going to bother some of you. Don't let it. This is a constant. I don't know if it's positive or negative, but this is the opposite of that constant. I don't know if that's going to be positive or negative. I'm just going to account for it by always just tacking on a plus c. All right, so what we have then is that this function f looks like this, and actually that's the c is not what I need, is it? That's what I was just talking about earlier. This is really some g of y function. I just out of habit did the constant, so it's a g of y function. All right, so let's go back and differentiate f with respect to y now. With respect to y, so the derivative of y is 1 times this constant, e to the t. T e to the t, that doesn't have any y's in it. It's a constant, it's 0. The derivative of e to the t, that's a constant, it's 0. And the derivative of g of y is g prime. And so I'm going to equate that with everything up here. So that's going to be a 1 plus an e to the t. And so just like happened in the past, the e to the t's cancel out. I have just a g prime of y equal to 1, which means g of y is equal to y plus some constant c. There really is a constant. So finally, my f function, my f function is everything up here plus this g function that I just found. And once more, if you take that function and you differentiate with respect to t, you'll get this portion. If you take that function and differentiate with respect to y, you'll get that portion. All right, exact equations aren't too bad. They look lots worse than it is, but the procedure works the same every single time. So I've given you three problems for some homework. So I'll post those solutions, but please go through the practice with those and ask any questions about the partial derivatives.